Hello, my name is Gregory. I'm a PhD student at the Chair of Structural Mechanics and Monitoring at Düthé, Zurich. And I'll be talking about using machine learning to do some diagnosis of leading edge erosion on 2D airfoils. So maybe just a word about, well, first, just the content. So I'll just give a brief introduction and overview, then I'll show the data generation pipeline, I'll model architecture, go over the results, and then we'll conclude. So just a word about the Aerosense project, as my work takes place within this context. So within the Aerosense project, we're aiming to develop a first ever MEMS-based surface pressure system that we can apply to wind turbine blades, and we could then retrieve pressure fields on a operating wind turbine blade. And so just a word about leading edge erosion. So leading edge erosion is a problem which is increasingly becoming important as wind turbines become larger and wind farms age. And it, of course, reduces power production, increases noise, and can also affect, if you leave it go to the extreme, can affect the blade structural integrity. And current methods to diagnose leading edge erosion rely on manual or or drone-based visual inspection. You can also use vibration-based methods or SCADA analysis. And all of these methods are pretty limited for continuous monitoring. And also there's no methods based on aerodynamics. So within this Aerosense project, how can we use our MEMS-based pressure system to use the pressure around the blade to diagnose the extent of leading edge erosion? And so here's a quick overview of the method in itself. So as our Aerosense is not yet, well, it's still under development, we need to replicate the data that we would gather from the sensor. So for now, we're using this whole data generation pipeline, which I'll go into detail, and then we feed that, all the data set that we generate through this pipeline, I'll feed that into our machine learning method. And that gives us sort of roughness predictions, which we can then tie into leading edge erosion. So first up, to develop a robust data set, which is represented, which really we can say would happen in real life, we need to be able to generalize to any wind turbine, and we need to account for some warping or deformation of the blades and thus the shapes of the airfoils during the operation. And so we need to simulate a wide range of airfoil geometries. And so we would like to simulate this very diverse data set of airfoils, but how do we choose which ones? We want to avoid biasing the actual data sets, and we also don't want to just input random shapes. I mean, we want realistic airfoils. And so we decided to implement this airfoil shape variational autoencoder. And this VAE, this variational autoencoder, the idea is to train the generative model on the data set of a bunch of airfoils, and then we can actually sample from the latent space created during the training to create new airfoils. And why choose variational autoencoders? Well, VAEs are good for generative purposes, as they condition the latent space quite well for then sampling out of it and creating new, well, not new information, but creating these samples from the latent space. And here on the right-hand side, I show the VAE architecture. I won't go into too much detail, otherwise it will take quite a bit of time. But I just want to say that the decoder is based on parsec parametrization. So some of you may be familiar with this. It's a way to describe an airfoil and then to generate an airfoil from 11 parameters. And it's quite, it's pretty handy here as we always get smooth output airfoils by using this parametrization. And so once we train this shape, this VAE on this data set, which is quite widely available, then you can actually visualize the latent space. And so here I show this latent space using TSNE, which is a data reduction technique. And you can see that you really have these clusters of different airfoils where you have sort of the fatter ones to the left and the skinnier ones on the right-hand side, and the camber also places it differently throughout the latent space. And so then we want to use the generative procedure to actually, so we want to sample from this latent space to get a latent vector and then pass it through our trained decoder. And with that decoder, then we can get the airfoil shapes. So now that we have all these airfoil shapes, we also need to then actually handle the CFD inputs. And the way to do this is we want to, again, have a robust data set. So we need to generalize to a wide variety of inflow conditions. And to do so, we have, we take some pretty standard distributions for the various variables that we input. So the wind speed, the angle of attack, turbulence intensity. And to simulate the roughness, which is the prediction goal and thus leading edge erosion, we actually have a model where we have 4 patches at the leading edge of our airfoil, and we then sample from a truncated half-normal distribution to get the roughness height for each patch. Then we can do some some validation on our CFD model. So we're using an OpenFOAM 2D K omega SST LM model, and the changes in the surface sand-grade roughness that I've just talked about now, they should replicate the leading edge erosion. And we do some validation where we show that the trends in the pressure distributions match previous experimental work by this author here. So just a brief summary of the data generation pipeline. So we're going from our airfoil shape generation via the VAE. We mesh the shapes, and at the same time we sample the CFD inputs. We run it through OpenFOAM, and then we store the data set at the end. Now, once we want to use the data, there's a number of ways that we can actually represent the data, and the way of doing so, the data substrate, if you want, has quite a big impact on not only the machine learning architecture, but also the performance. And there's a number of solutions. Either we can use arrays, point clouds, or graphs. And we choose to use the point cloud representation as it's quite simple, but it's also quite efficient. And there's quite a few different point cloud machine learning architectures that we could use. So to go into detail on our machine learning architecture, which is based on PointNet. So for PointNet, we have 2 transforms which are permutation invariant, and there are 2 shared multilayer perceptrons and 1 output multilayer perceptron. And at the end of all this process, you get the however many output values that we would like to get based on the input. And our architecture is also, so this is the architecture that I showed now is based on, it's for one of these 2 modules that I show here. And we have a 2-stage model where we have, on the one hand, a flow estimator module, and on the other hand, a roughness predictor module. And the flow estimator, the goal is here to gather information about the inflow conditions, so angle of attack, inflow velocity, turbulence conditions. And this then modulates the prediction from the roughness predictor. And why we've decided, we could combine everything in one big neural network, but why we decide to actually separate the 2 is because it'd be interesting to actually test different methods to estimate the flow parameters. And one such method is given by my colleague of Aerosense, Julien Depardet, who's developing a method, an analytical method based on curve fitting to actually get the angle of attack and inflow velocities. So the roughness predictor there is based on point net in this instance. And so just some results. So we have trained this on an initial prototype data set, which has 300 CFD simulations. And in this data set, we use the same value of roughness for all patches, just as a way of checking that everything is okay-ish. We don't want to make it too hard just in this small data set, the small prototype data set. And so we use 240 samples for training and 60 for validation. And here I show on the right-hand side 15 roughness predictions from the validation set. And you can see that overall the results are quite promising, but there's a few things. First of all, we often overpredict the roughness, and and the predictions are often quite bad for small roughness values. And the possible causes for this overprediction, it could be on the one hand due to this tiny data set we have. I mean, 300 samples is not enough. We need to really generate more data. But we can also see that the small increases in roughness, they have quite a minor impact on the pressure field. And that small impact might be hard to detect. And this is why we need more data, but we also might need a more accurate CFD model, as the one we're using right now it's not a model which actually accounts for roughness in the turbulent boundary layer. And so the solutions to this are, on the one hand, we need to generate more data and use a larger data set, but we also need to, we maybe need to adjust the distribution of the roughness, as we might want more samples in our data set which are coming are for small roughness values, as this seems to be what is more hard to detect, and thus we want to show it more often to the network. And like I said before, we would also like to maybe use a more accurate CFD model. So to conclude, we developed a pipeline to create a robust data set which replicates a wide range of operational conditions, which then we use CFD on diverse airfoil geometries via this generative machine learning framework. And we are, with this data pipeline, we're aiming to introduce as little exclusion bias as possible. And we also, then in the machine learning approach, we used a split two-stage approach, which given a pressure field around an airfoil, we want to, on the one hand, predict the flow conditions, but we also want to predict the roughness at the leading edge of the airfoil, which we can then tie into the actual leading edge erosion. And then, so for future work, like I said before, we need to generate a full data set. We need to increase the accuracy of the CFD model, and we also need to test and compare multiple machine learning architectures and maybe the analytical flow estimator that my colleague is developing. So thank you for your attention. I'm open to any questions, and just want to mention my fellow AeroSense colleagues. So there's Julien Depardieu, who presented today, Yuri Murakovsky, and Tommaso Polinelli, who is presenting on Friday. And I also want to thank the Swiss National Science Foundation, the INOSIS bridge, the bridge agency within the Swiss National Science Foundation. All right, I'm open to any questions.
Thank you very much, Gregory. It would be odd to ask you questions since we are involved in this research. So maybe we could ask the audience again, if you have questions for what Gregory presented, to ask in the Q&A. Until we get a question, maybe just to give you the chance to elaborate on a point, or maybe on what is the next step, might be nice to elaborate on here.
So as I said, obviously the immediate next step is to create a bigger data set. Right now, this prototype data set, I mean, it was really just to check that everything is training properly, everything is functioning, and the method has potential. And right now, what we see that is learning, and we are getting some results, although albeit with quite a bit of overprediction. So that's the immediate next step. And then also we would like to maybe get a more accurate CFD model, which accounts for the roughness within the transition, within the turbulent transition of the boundary layer. Yeah.
Mm-hmm.
Okay, thank you, Gregory. There's a question that came over, and the question is, thank you for the presentation. How did you implement the roughness of the surface in the open foam model? What kind of module did you use in it?
So that's a good question. So we haven't modeled the roughness in a physical way. We're modifying the wall functions actually. So they're just the sand-grain, the equivalent sand-grain roughness of the wall functions. And so the plan is also to use a modified then version of the K omega SST model, which accounts for this roughness within the transition boundary, like I said before. But right now it's this roughness just impacts the flow conditions, and then so it's not physically modeled. It's within the wall function.
By physically, you mean you did not change the actual geometry?
We didn't change the geometry, just not the mesh in itself, just the geometry stays the same. And the reason for this is we didn't want to create meshing dependency issues within. We didn't want meshing dependency to arise within the data set, right? So we want to avoid manually tuning the mesh ourselves. So we would only keep that as automatic as possible and not then have mesh dependency issues within the data set.
There is maybe a further question we can take in a few, I would say quickly, as we're approaching the end of this part of the session. So it's how did you verify that the change in the wall model is a good representation of the roughness?
So this, I talked about it quite briefly here. Find it here, where we are validating our CFD model. So we validated that the trends in the pressure distribution match the trends in the roughness. So there's quite a few experimental work in the experimental results where we can then fine tune the roughness values of our wall function to match the actual behavior that we would see in the pressure distribution.
Mm-hmm.
And this is one of the studies that you use from Maniaci.
Yeah.
There are a few others also evident.
Yes.
And maybe I ask you to give a closing statement of linking the framework that you just showed with the actual instrumentation of the AeroSense, if you want to remind us of that, which is the goal.
So I can just go back to the...
And we can close with that I think we need a buffer for the next session, but we have time for this note.
Just a quick note on AeroSense. So like I said, we're trying to replicate with this whole data generation pipeline the output of AeroSense, right? So AeroSense should give us the pressure of a field surrounding, along a slice of a blade, right? Mm-hmm. And so an airfoil. And we're trying to replicate this output with this whole data generation pipeline. And so we're hoping that we can not only use these pressure measurements, but then also one other attribute of the AeroSense system that it will be measuring acoustic. It will also do acoustic measurements. So we'd be able to then use that to maybe add a bit of information, especially for the boundary layer. So the turbulence within the boundary layer. So we could use the acoustic measurements to actually fine tune how the boundary layer behaves, right? And then we could correlate that back to our model that we're using now.
One final aspect is the fact that a lot of the pieces that Gregory built will also go into a digital twin that is part of the Airfoil project. So they're not just for fun and generating data; they will also be part of a digital twin system as well.
Yes, exactly. So my colleague Yuri Marikowski is working on the whole digital twin aspect, and my framework, all that I'm developing within the machine learning part of this project, will then integrate within the digital twin that Yuri is working on.
Mm-hmm. Okay, so thank you very much, Gregory. I think